do one. All right, so example 5, picking up with infinite power series. It says if f of x is equal to this little series here, and they give us the general term or the nth term there, and big F of x is equal to the integral of little f of x, and if big F of 0 equals 1, find f of x. Okay, no big deal. So how am I going to find big F of x? Well, I'm going to start by saying that big F of x is the integral of little f of x. And there's two ways to do this, remember. You could do this as an indefinite integral and put your plus c, and then you can use the initial condition to find c. And then once you have that, then you can go ahead and use it to find, well, that's what, it's not asking us to evaluate it, it's something else. So that is how we're going to do it. All right, so let's go ahead and replace f of x now with the infinite series, negative x plus x cubed over 3 factorial, bless you, x to the 5th over 5 factorial plus dot, 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 plus negative 1 to the n plus 1, x to the 2n plus 1. I'm going to include the general term in here, 2n plus 1 factorial plus dot, 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 close parentheses, dx. All right, nice. Now, with infinitely many terms, you should be able to integrate this pretty quickly, right? Yes, and down the line, term by term. All right, good one, good one. All right, so let's go ahead. What would be the antiderivative of negative x? Well, it'd be negative 1/2 x squared. Yeah, plus, this would be x to the 4th all over 4 times 3 factorial, minus x to the 6th over 6 times 5 factorial, plus dot, 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 plus negative 1 to the n plus 1. And now I'm going to highlight that because when I integrate and when I differentiate, I could throw off the balance of the sign change. So I'm going to come back and check that. But I can go ahead and integrate like I did the others. I take the x and I add 1 to the exponent. So what's 2n plus 1 plus 1? 2n plus 2. And then I divide by the new exponent, 2x plus 2. And then I put the coefficient that was there already, which is 2n plus 1 factorial on the bottom. And then plus dot, dot, dot. And then what are we going to have to put eventually? Plus c. So now plus c. Good. Now, here's the deal. You notice how the polynomial that we just integrated, it's listed in increasing order. A constant is really degree 0. So normally when we put the plus c at the back, it's because something is in decreasing order. It might be wise then, as we rewrite it on the next line, to bring c to the front, okay? Because it is your constant, right? Now, if I simplify this, I get minus x squared over 2. But I'm going to look for a pattern here. Isn't 2 the same as 2 factorial? Yeah, it is. Plus, the next term is x to the 4th over, what's 4 times 3 factorial? Isn't that 4 factorial? Yep. And then minus x to the 6th, 6 times 5 factorial, that's 6 factorial, plus dot, 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 plus, and then I got my alternator that I still have to check. I will check it. And then I can simplify this to x to the 2n plus 2 all over, and using the pattern, that should be 2n plus 2 factorial, and then plus dot, dot, dot. Now let's check the alternator real quickly here. Notice when I generate a 2 on this negative 1/2 x squared, what n does that associate with? It would have to be a 0, right? So that's 2 times 0 is 0. 0 plus 2 is 2. That would give me the 2. So I want that term to be negative. So when I let n equal 0, does that give me a negative in my alternator? 0 plus 1 is negative 1. It does. Okay, so that matches. That's good. You want to make sure you check that, because if it weren't, if I was out of step, I would just take the plus 1 away and call it to the nth power. All right, so that looks good. Now, how do we find the value of c? I need an initial condition, right? And we're given this. We're told that f of 0 equals 1. So it's like what we did before. We're just doing it for infinitely many terms and a general or nth term. So we'll say at the point 0, 1, colon, and we plug in and we get 1 equals c. minus 0 plus 0 minus 0 plus, guess what it's going to be all the way down the line? Zeros, right? Wow, that was nice. So C equals 1. So I plug that back into above, and I get the particular solution that big F of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot 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 plus negative 1 to the n plus 1. I'll put that in the top with the x to the 2n plus 2 all over 2n plus 2 factorial plus dot dot dot. Wow, okay. Now just to review, when I integrate a power series like I just did, do I change the radius of convergence? No, I don't change the radius, but I do possibly change the interval of convergence, right? It's the endpoints that might fall by the wayside or be included possibly. So I would have to check the endpoints. But the follow-up question to this is, hey, do you recognize big F of x? It's cosine. Yes, this is cosine of x, right? Perfectly cosine. Now, is this the nth term that we memorized the other day for cosine? No, but does it work? Does it still capture the pattern? Yeah. We learned just x to the 2n over 2n quantity factorial, but plus 2 is not a big deal. Yeah, I do need the alternator. Yeah, I do need, and we've already checked it to make sure it matches up with this right here. So yeah, so this is not the general term that we prefer for cosine, but it works. It captures the pattern. So we can manipulate the nth term or the general term just like we would, anything else. So if I integrated to get cosine, what would the function f of x be? Because notice it looked like it was sine, doesn't it? Oh my God. But it's out of step by a half. So it's the opposite of sine. Yeah, there you go. What's the antiderivative then of negative sine? Cosine. That's just what we kind of proved, right? In Taylor series form. Yeah. It is kind of cool. All right. And do we need to worry about testing the endpoints? What's the interval of convergence for sine and cosine? All real numbers. Good. So we don't need to worry about testing the endpoints. I just want to remind you that if it did have, a shortened interval of convergence, we would have to retest the endpoints if it was asked for it. Okay. All right. So that's cool. I just wanted y'all to be aware of that it works. It works with power series and the general term. All right. Example 6. Find a Maclaurin series for sine of x squared. Write the first 4 non-zero terms and the general term. Got it. No problem. Are we going to recreate the wheel, reinvent the wheel with Taylor's coefficient rule? No. We're going to use our sine of x. So let's go ahead and write sine of x. What's the first term in sine of x? Sine of is an odd function. So x, good. And then minus x cubed over 3 factorial. It says the first non-zero term. So then plus x to the 5th over 5 factorial. We'll do one more. X to the 7th over 7 factorial. Plus yada, 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 plus, now let's go ahead and include the general term here. Negative 1 to the n or n plus 1. I'll come back and check that. But it should be odd power, so that's 2n plus 1. And then it's divided by 2n plus 1 factorial plus dot, dot, dot. So notice sometimes that alternator, negative 1 to the n or n plus 1, sometimes we put it out front, by itself. Sometimes he just wants to belong, feel important. So we put them as a factor in the numerator. It's really the same. Okay, let's check the sign to make sure it works. In order to get x to the first, I need this n to be a what? To get x to the first? 0. So when x is 0, or when n is 0, I get positive x to the first. Let's make sure it's positive when n is 0. What's negative 1 to the 0? Positive 1, right? So it works, right? Again, if I had been out of step and I got the wrong sign, just put a plus 1 or a minus 1 there, and that'll alternate the alternators. Does that make sense? Yeah. Yeah, it delays it. Yeah. Okay. So there we go. So now we can say f of x which is sine of x squared. All we got to go through now is, or all we got to do is go through and replace x with x squared. So can we do that in one step, or do you want to do it in two steps? One step. Okay. So just remember, when we raise a power to a power, we don't add the exponents, we multiply. Yeah. So it's going to be x squared minus x squared cubed is x to the 6 over 3 factorial, plus x squared to the 5th is x to the 10th over 5 factorial, minus x squared to the 7th is x to the 14th over 7 factorial, plus yada, 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 plus, and we'll do the same thing here, negative 1 to the n. This becomes x to the 2nd. I might do this one in two steps, to the 2n plus 1, all over 2n plus 1 factorial plus yada, yada, yada. Now, you wouldn't necessarily have to simplify your general term. So if this were a free response question, it'd be hands off. Count the number of terms. You have 4 non-zero terms. Yeah. Do you have the general term? Yeah. Do you have an equal sign and then yada, yada, yadas on either side of the general term? Yeah. Now, if this were a multiple choice, the general term would probably simplify down to, what would it be? What's x squared to the 2n plus 1 power? X to the 4n plus 2. Yeah, yeah. All over 2n plus 1. So, you know, if you could have done that as you wrote it down, that's fine too. But notice how having the general term there in the beginning is a really good idea. It didn't say that we had to write the general term on this line. It just said in the very end, we needed the general term. But it would have been a lot harder to just say, okay, I'm just going to take the first 4 non-zero terms, get this, and now on my own, I'm going to try and write a pattern that generates that. No, thank you. That's going to be a little bit harder. So if I know what the pattern is for the simpler thing, I can just do the same thing to it as I do with all the other terms. And then the nth term of the pattern is already there. Okay. Yeah. So include it from the very beginning. And the interval of convergence should be all real numbers again, because it's x squared. It's a sine function. All right. So don't reinvent the wheel. Use the sine, cosine, and e to the x. And then later on, there's one more, 1 over 1 minus x. All right. Any questions on 6? Just trying to get comfortable and familiar with these things. All right. Example 7. Find the Mac Daddy series for x cosine of x. Again, the first 4 non-zero terms and the general term. So this is another thing we could do. We can replace x with a function of x. We can't change the center. So if you had to write a series like at a different center, now you got to reinvent the wheel with Taylor's rule. But here we can, right? So let's go ahead and write out cosine of x. And I'm not going to call cosine of x g of x because it isn't. Cosine is the even function. So just to review, it starts with 1 and then minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. There's 4 non-zero terms plus yada, 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 plus, and then we got our alternator, negative 1 to the n. I'll check that. And it's just even powers. So x to the 2n all over 2n quantity factorial plus yada, yada, yada. And now in order to get a 1 in the first term, n has to be 0. And negative 1 to the 0 is positive. So that does fit. That's good. We don't have to delay it, as you said, add a plus or minus 1 to the exponent. All right. And now we'll just say, okay, g of x is x cosine of x. And all we got to do now is distribute x all the way down the line towards infinity. So here we go. We get x minus x cubed over 3 factorial, oh, sorry, 2 factorial.
You only distribute it.
Yeah, you distribute it. What's that? No. Yeah, it's x over 1. So you just multiply your x's together. So plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial plus dot, 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 plus negative 1 to the n. Again, I always come back and check that n just to make sure. And then I get x to the what? What's the new power? Is it 3n? It's x to the 1st times x to the 2n. Yeah, good. It's 2n plus 1. All over the quantity 2n factorial plus yada, yada, yada. And then if I check the alternator, I'll put it off to this. Well, I'll put it in the numerator. the first term has to be x, so that's going to again be when n is 0, and -1 to the 0 is positive, so that works. Okay. All right, so again, including the general term in your original cosine makes it so much easier to just find the general term when you change it, instead of having to again write these down and say, I got this, I can see the pattern there in terms of n, and then you come up with this on your own. Okay. All right. Be careful, like if it asks you to find the derivative of something like cosine and write the first four non-zero terms. We saw this yesterday. But in this case, if you took the derivative of 1, it would go to 0. And now you only have 3 terms listed. So you would want to make sure that you tack on another term. Because if you know the pattern, what's that? No. If it asks for the interval, yeah. This one is x times cosine, so it should be all real numbers. But this one it's not purely a cosine function, so you would have to actually prove it. Yeah. But it should be all real numbers again, because x is also continuous everywhere, so it doesn't affect it that much. All right, number 8 is an interesting one. It has kind of an interesting application on the back end of the problem that you don't have to worry yourself about. But anyway, we'll approach it from our perspective, and then we'll talk about it in general. Find the Maclaurin series for this. All right, I'm going to let you do this one, but let's map out the strategy first. Do we know what the Maclaurin series is for e to the x?
We do.
Yes. Can we then from there create the Maclaurin series for e to the negative x?
Yes.
Yes. How will I add those two guys together?
Oh my God.
Should I add them together linearly like this? Term, plus term.
Term plus term. Term plus
This is how we should probably add them vertimously,
term.
because aren't the terms going to look very similar? Yeah. But you'll notice that when you replace x with negative x, every other term is going to be negative. And so you're going to get like every other term canceling out. Once you get e to the x plus e to the negative x, then distribute the 1/2 all the way through to come up with your final line. Okay, go ahead and do that. And I'm going to take attendance and pause the video while y'all generate that. All right, so here we go. E to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... plus, well, I would include the general term the whole time because it asks for the general or the nth term in the end. Now, you might be able to get lucky and figure out the intrinsic pattern and write a formula for it, but if not, it's safe to do this. It's x to the n over n factorial plus ... Now, again, that we're assuming here that we're starting with n equals 0 because that's how we generate the first term, but you don't have to state that here. It could be that we start with n equals 1 or n equals 5. It only matters that you state where you're starting when you put it in sigma notation. All right, now e to the negative x, you go through everything with an odd exponent will change signs. Everything with an even exponent stays the same. So minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus ... plus. Now this is going to have an alternator, -1 to the n times x to the n times n factorial plus ... And let's see, when I plug in a 0, I get a positive term. So that works well. And now I'm going to add these vertically. So that gives me e to the x plus e to the negative x. And if you notice, all of the odd terms cancel out. And then I add what's left, and I get 1 plus 1 is 2, plus I have 2 of those. And then if I do more, I'm going to have plus 2 of these over 4 factorial plus ... Now, how do these add together? That's going to be kind of a harder thing to manage, right? Yeah, well, I notice here that when I add them together, all the negative terms are gone. So when I add them together, the alternator could be gone. So it'd just be 2 x to the n over n factorial plus ... Now I notice here I only have 3 terms. That's okay. That's not my final. It's not my final thing. If I wanted to add another term there, I could. But now let's multiply through by 1/2. So 1/2 e to the x plus e to the negative x, which is the same as dividing by 2. Notice all those 2's get wiped out. You're left with 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial plus, I need to add a term. Oh, crap. Do I come up here and add another one and subtract, or do I see the pattern? Yeah, I see it. It's x to the 6 over 6 factorial plus dot, 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 plus, and then that 2 is gone, x to the n over n factorial plus dot, dot, dot.
What do you?
Oh, it's x to the 2n. Sorry, my bad. I didn't even write that way up here. Yeah, no, my bad. It's x to the 2n. Yeah, so this didn't quite work with the general term. It almost confused me, right? But at the end, if I had not put that up here, just draw a line through it. You could see the pattern at the end. In fact, this looks a whole lot like what? It looks like cosine, but it's not cosine because cosine alternates and this one doesn't. Okay. This one is called a catenary curve. Catenary curve. Yes, sorry. Yeah, it is. I wasn't paying much attention at the end. Typical me. Typical me. Typical me. Okay, so there you go. Yeah, a catenary curve. Has anyone been to St. Louis and seen the Gateway Arch or the St. Louis Arch? Didn't one of you go up in it? Yeah, you did, right. The Gateway Arch is the most famously misidentified parabola in the whole wide world. It's not a parabola. It looks like a parabola. It's not. It's actually an inverted catenary curve. Okay. Did it say that on the sign at the bottom? Did you read the sign? Did it say catenary curve? I hope so. I hope it didn't say a downward opening parabola. Oh, that's a beautiful picture. Can you send me that? I want to put that in the notes for this for next year. Yeah. Okay. So what's a catenary curve? A catenary curve, this one is an inverted catenary curve. The function that we're looking at here looks like this. Okay. What's different about a catenary curve? A catenary curve is basically the shape you would get if you hang a weighted rope. Okay. It's the effect that gravity would have on that weighted rope. Okay. So it looks like a parabola, but the parabola is going to be what's created when gravity pulls on it after it goes upward. Let me get back to what I was doing. Okay. If you throw something up, it'll come back down according to a parabola. But if you suspend a weighted chain or a weighted rope, the shape is not a parabola. It's a catenary curve. And if you invert it, you get the inverted St. Louis Arch. So what's quite the difference? Well, it has to do with near the vertex. A parabola is a little bit faster. It changes faster near the vertex. Whereas a catenary curve is more slow to change, right? If you look at the graph of the one that I had up here, notice it kind of looks like a lazy x squared, right? It's sagging, but notice the y values here are quite dramatically different. So it's a much more gradual fall if you scaled it the same way. So that's what a catenary curve is. It's the shape that a weighted chain or rope would make due to gravity. Flip it upside down, you got yourself a national icon, right? Now, there's another name for this function. This function is actually equal to not cosine of x, but cosh of x. It's another name.
That's 7.1.
Right. Now, what does cosh of x stand for? This is called hyperbolic. What'd you say? Hyperbolic cosine.
Is there chinch?
There's all of them. There's sine h of x, cosine h of x, tangent h of x. Yeah. The trig functions that we look at are called circular trig functions.
Oh, and these aren't circular?
No. Yeah. Ours are derived from the circle. These are derived from a hyperbola. Okay. A hyperbola is like two parabolas that come at each other. Come at me, bro. Okay. So there are angles in trigonometry associated. And that's what the H stands for. And it's kind of cool because the derivative of sine, hyperbolic sine, is still hyperbolic cosine, right? But the derivative, interestingly enough, of hyperbolic cosine is actually Regular, no, it's not negative. It's regular hyperbolic sine. There's no rule that says when it's negative, it has co in it, it's going to be negative. Okay. Yeah, you can actually verify that by taking the derivative of what we just came up with, and they'll all be positive terms, and that's hyperbolic sine. Okay.
Do Catenary Curve only actually was going with the.
Yes, once you get the shape, you can flip it, but to create the shape like in nature, you have to suspend something and let it sag. Yeah, the catenary curve is basically the shape from something that sags, whereas a parabola is the effect that gravity makes on something that goes up and comes down. Okay.
Like you'd have to manipulate it for it to be like.
Yeah, you'd have to put, yeah, you could easily reflect it just by putting a negative in the front. And that, yeah. Uh-oh. Oh, I'm leaning on. Okay, there we go. All right, cool. So I just want to throw that out there. If you go on to take higher level math, like Cal 3, you'll talk about the hyperbolic trig functions. Yeah, cost too much. There you go. Yeah, everyone calls them cosh of x and sinh of x and all that. Okay, now do we have time for this? I hope so. This is my favorite equation in the whole world. Again, if I were to get a tattoo of math, this would be it. I like to put it as pi I, but if you look it up on the internet, it'll always be I pi. I don't like that either. I like to flip it around. I like to call it pi I. Commutative property multiplication, it's my prerogative. You do what you want to do. You want to be a sheep and call it eat it I pi, you go for it. I'm a wolf over here, baby. Now, what makes it beautiful is not only is it true, it's actually a true statement, and it's true for all values, but as I mentioned earlier, it has the basic building blocks or the basic operations in math. We have addition, which is really also subtraction. We have multiplication, which is also division. And then we have exponentiation, which is like rooting. So those are the three main operations: add, multiply, and exponentiate. And it also has then the basic elements. It has 1, the identity element of multiplication. It has 0, the identity element of addition. It has E, the analysis base, Euler's number, which is what we use in calculus. It has pi, the geometry's transcendental number that comes from the shapes. And then we have I, the imaginary unit, which is not imaginary at all. Your cell phones in electric engineering use I all the time. So it has all the building blocks in it, and it's so concise and precise, and it's just beautiful. I love it. So what we're going to do is we're going to derive this for you, or I'm going to derive it with you, I should say. All right. So here's how we're going to derive it. Lop it. Well, what we're going to do is we're going to come up with, can we do what we just did? Oh, you want to, okay. So let's do, if you look at e to the x times I, this is why it's typically written as I pi, because when you write it as xi, x is your variable, and you can write it as I times x. Okay. So yeah, I think we could try that, Lauren. Let's try it. So what is, nah. All right. So e to the x, of course, is 1 plus x plus, I'm glad you're awake, Ethan. Yeah. Yeah. X cubed over 3 factorial. I'll go one more. X to the 4th over 4 factorial plus yada, yada, yada. Okay. So there's that. We're not going to need the general term here. Now we're going to replace x with ix, which is the imaginary unit. Now, if you've forgotten about I is the square root of -1. I squared is -1. I cubed is -I. I to the 4th is back to +1. So I to the 5th is back to I. They repeat in cycles of 4. Okay, they repeat in cycles of 4. And if you divide by 4, the remainder is your new exponent, essentially. Okay, so
item 6 is where.
well, yeah, let's go through and do it like this first. Let's just put parentheses. 3 factorial plus to the 4th over 4 factorial. I'll do one more to the 5th over 5 factorial. And now I'll go through and I'll put I in there. I plus ... right? So that's going to be 1 plus I, and then I squared is -1, right? Oh, I still need the X. Yeah, I forgot the X. Yeah, that, I was saying that's not good. That's not good. Still need the X there. I still need the X here. I still need the X. Still need the X. Yeah. So this becomes plus I squared is -1, so that becomes a -1. So we get minus X squared over 2 factorial. And then I cubed is -I, so this becomes minus I times X cubed over 3 factorial. I to the 4th is 1, so now it's back to plus X to the 4th over 4 factorial. I to the 5th is the same as I, so now it's plus I X to the 5th over 5 factorial. Let's do one more here. I want to add a couple more terms. So the next term would be plus up here, I X to the 6th over 6 factorial, and we'll do one more, plus I X to the 7th over 7 factorial, plus dot, dot, dot. So what would the next one be? Okay, so we've already done the 5th power, the 6th power. I to the 6th is the same as I squared, right? 6 divided by 4 leaves a remainder of 2. So it's equivalent to I squared, which is -1. So that's going to be negative X to the 6th over 6 factorial. I to the 7th, when you divide by 4, the remainder is 3. So it's equivalent to I cubed, which is equivalent to -I. So I get -I X to the 7th over 7 factorial plus dot, dot, dot. All right, now what are we going to do? Well, good question. If you notice now, every other term has I in it. Is this an alternating series? Yeah, it's not an alternating series because an alternating series alternates on consecutive terms. Yeah, this has pairs, right? Plus, plus, minus, minus, plus, plus, minus, minus. And then every other term has I's in it. So here's what we're going to do. We're going to separate the I terms from the non-I terms. So let's write the ones I didn't highlight first. 1 minus X squared over 2 factorial plus X to the 4th over 4 factorial. Right? And then it'll be minus X to the 6th over 6 factorial plus yada, yada, yada. Okay. And now plus, I'll pick back up with the I terms, and I'm going to factor out the I from all the terms that I highlighted. I parentheses, and then I'm going to get X minus X cubed over 3 factorial plus X to the 5th over 5 factorial minus X to the 7th over 7 factorial plus yada, 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 close parenthesis, plus yada, yada, yada. All right, so all I did is I grouped the non-highlighted terms together in front, plus yada, yada, yada. And then the ones that I highlighted, I noticed they all had an I in it. So I factored it out and just wrote the highlighted terms without the I, plus yada, yada, yada. Close parentheses, plus yada, yada, yada. Plus yada, yada, yada. So on and so forth. Now, if you stare hard and long enough, you're going to recognize something. You're staring? Yeah, all the terms without an I. What's up, old friend? That's circular, not hyperbolic. What? That's cosine of X. Yeah, yeah. Plus I times hola, amigo. What, once I factor out an I, what's left in there? Sine of X. Whoa. So look what we have. We have E to the IX equaling cosine of X plus I times sine of X. This was really Euler's breakthrough right here.
We live in a simulation. There's no way that happens and someone didn't program it.
Well, that's when you go back to your thing about.
Yeah. So now I want to evaluate this function at pi. So at x equals pi, you get e to the I pi or pi I, as I just prefer to write it. But I can see why people sheepishly call it I pi. Okay. And then we get, yeah, because x is your variable and you're plugging it in. We typically write coefficients in the front of the variable, typically. And this becomes cosine of pi plus I times sine of pi. Well, guess what time it is? It's unit circle time, everybody. So I got cosine of pi and sine of pi. So e to the pi I, what's cosine of pi? No, not 1. -1. And what's sine of pi? 0. So I get I times 0. Well, guess what I times 0 is? 0. And so now if I simply just tidy up a bit by adding 1 to both sides, I get e to the pi I plus 1 equals 0. Drop the stylus. Boom. And there it is. I don't get it. Euler didn't either. He was just getting used to symbols. He's like, I guess this works. I don't know. All right, what's for dinner, honey? Yeah.
Wait,
Yeah.
you actually think that it's
Yeah. This is actually deriving Euler's identity using the infinite power series, the Maclaurin series for e to the x. Yeah. So there you go. There's the name. So now if you wear the tattoo or the shirt or whatever, you can tell people about it. Hey, you have time? Sit down. Let me talk to you a little bit about this. Right. So yeah, this goes on to what I was talking about, the cosmological argument. Yeah.
It's so cool.
For the existence. Yeah. Existence
That exists.
of a whatever you call that God, a divine creator, right?
Because it can't just human nature.
That's exactly right. The equation is too perfect, like the watch that you're wearing on your wrist, iWatch, like an automobile. It's too perfect. It's too the likelihood of those parts just falling into that configuration by chance is 0. And this equation is like that watch. It's like the watch of the car. It's so precisely accurate that someone had to create this. And who do you give to, what name do you give to that equation maker? Leonard Euler, right? Leonard Euler. Now I shall be less distracted. So anyway, yeah, this is actually pretty good. This is actually good stuff right here.
Maybe you should get this entire thing tattooed. Like
I
down your
did
back.
see someone who had this entire thing tattooed on their arm. Yeah, the whole thing. It was all the way down there. It was on a meme. Like, I don't know the person personally, but I saw the meme and it was all the way down the arm. I'll see if I can find it on my phone and I'll put it in here. But yeah.
Really?
You know, this guy was on little graphs where it's like those graphs where it's like when you're studying
Right.
something and then it's like how much
Yes,
you
we
know,
went
how
from
much
this giant mess
how much
to
you
something
realize
so
you-
beautiful
it just
that
happens.
has so many beautiful parts to it that are significant. Nothing in this equation is not supposed to be there. Everything that's there serves a really, really important purpose and has a really, really profound meaning. So anyway, yeah,
Jensen.
imagine skipping. All right, Jensen, I hope you're watching the video. Right. All right, we're done with 9.3. Be working on the worksheet for 9.3 and get it in as fast as you can.
Hey,
Worksheet 9.2, we'll make due Friday.
Nice question. What is the equal?
Derive it, yeah. And then worksheet 9.3, let's do it by, I guess, next Tuesday or something. Yeah, somewhere. All right. So there's really only 2 more sections to go, and they go pretty quickly. The next section is just geometric series specifically, and then the last section is like the alternating series error, but it's for all polynomials. It's called Lagrange error bound. Okay, and that's it. And then we'll backtrack. All right.